Alright, welcome back. So in this video we'll be talking about an introduction to hypothesis testing. Alright, hypothesis testing is another method of statistical inference, right? We know what inference is, using a sample to figure something out about the population that it came from. Okay, so far we've talked about point estimation. That's our simplest version of inference. Right? Then we built off that to look at confidence intervals. Now we're going to start talking about hypothesis tests. Okay, and then eventually we're using all of these different statistics to estimate whatever our parameter of interest might be. All right, so first of all, so hopefully you already have a pretty good idea in mind what the idea of a confidence interval is. Right? What a confidence interval says, we have no idea what this parameter is, so we want to estimate it. All right, but on the other hand, a hypothesis test says, I think I've got an idea what this parameter might be. Let me collect a sample and see, does the sample that I collected, does it agree with this claim? Does it support that claim? Maybe does it refute that claim? All right, it's important going in because there's lots of crossover between terminology and stuff like this between confidence intervals and hypothesis tests, right? But it's important going in to recognize that these two things have different functions and they're answering two completely different questions, right? A confidence interval, I have no idea what this parameter is, I want to estimate it. A hypothesis test, I might know what it is. Does my sample data confirm that or refute that? Alright, so let's think about an example to demonstrate why do we even need hypothesis testing? Okay, what's the point here? Well, we know, I think it's pretty generally accepted, right, that people should get about 8 hours of sleep per night. Right? So maybe your claim or your hypothesis, you're thinking that you and your friends, maybe just students in general, don't get enough sleep. They don't get to that recommended 8 hours. All right, so you want to actually test this, right? You want to measure people's sleep, maybe ask them about their sleep or make them wear a device, a Fitbit, whatever, in order to measure their sleep, right? And you want to actually prove this. Okay, so the big question then is, at least in this scenario, how much sleep, right? So you'd be taking a sample and you'd find their average night's sleep, right? So how much sleep on average would this group of students that you're getting have to get less than 8 hours, right? How much less would that have to be to actually prove to you or to convince someone else, right, that your hypothesis is true or is correct? Remember, your hypothesis is that students aren't getting enough sleep, right? So what's the actual value that would convince someone of that? And maybe the value that would convince you be different than the value that would convince someone else. Okay, so these are important questions to think about. And these big questions are what a hypothesis test actually does for us. It provides a framework and a formal way, a formal procedure to answer some of those questions. So in general, it can provide you with what is this value, right? What is this cutoff value for evidence? What makes evidence for your hypothesis enough evidence to say, yes, there's actually something going on here, right? And then, but then also, how do we answer, because we know that with based on the rules of probability, sampling, sample distributions, all of this, right, we know that the sample that we take is one of many that we could have potentially gotten. Right? So the other big question, besides where do I set this cutoff, is, well, how do I know that this sample that I got is a good sample? How do I know that it can speak for the entire population? Right? Maybe I just got a weird sample. Okay, so how are my results? How do I know I can rely on my results? Alright, so these are the kinds of things that the hypothesis test helps us do. So really what a hypothesis test is it's a formal process, it's a formal framework for evaluating evidence and making decisions. Alright, so the first step in a hypothesis test, of course, is going to be we got to state our hypotheses. Right? Notice it says hypotheses, plural. And we also see something here about our significance level. So we'll see what that is. So basically step one is just set everything up. Step two is to calculate what's called your test statistic. All right, now if this may involve collecting your own data, or it may not. If you're working in a textbook type problem, it'll just give you the data. Right, but step two is where we calculate what's called our test statistic. Okay, this is where we start to evaluate the data. Then we got to make our decision. All right, we make our decision there's two different methods that we can use to make our decision here, which we'll look at. And then finally, right, we put our conclusion back in the context of our question. Okay, so let's start at step one. And notice it said hypotheses, plural. Right? We know what a hypothesis is. Right? In a statistical hypothesis test, there are two hypotheses. There's your null hypothesis, right, denoted as H0 or H0, and there's your alternative hypothesis. Right? It's denoted as HA or sometimes as H. So let's start by talking about our null hypothesis, because of course that's going to be our starting point. Alright, so this is your kind of conservative claim, your starting point. Right? Our null hypothesis is what we have to assume is true from the beginning in order to show that our hypothesis is true. Okay, the hypothesis test, the whole idea is we assume something is true and then try to prove otherwise. Okay, so remember our example was that we thought students weren't getting enough sleep. So in order to show that they're not getting enough sleep, right, we would have to start by assuming that they are getting the recommended amount of sleep. Right? In other words, our null hypothesis for our example would be that mu is equal to 8, or 8. Your alternative, on the other hand, is your working hypothesis. Right? This is where we state what is the effect that we're looking for. Alright, so in our example, remember we had to assume, in order to show that they were getting less sleep than the recommended amount, we had to assume they were getting that recommended amount. Alright, so we would state less sleep in our alternative hypothesis like this, mu less than 8. Right, makes sense, less sleep, less than 8. In our example, we had what we would call a left-tailed test. All right, where our null was that mu is equal to some claimed value, our alternative was that mu is actually less than some value. Okay, well what if you think that like if in our example you think maybe old people get more than the recommended, your grandma gets more, right? Well maybe there you could run a right tail test, right? That would be that mu is equal to some number in the null, that same claim, that 8 hours. Your alternative would be that mu is actually greater than 8. What if you don't know? What if you're just looking for a general change or a general difference? You can also do what's called a two-tailed test. Right? The null is still that mu is equal to the claim, but the alternative is not that mu is less than some claim or greater than some claim. It's just that it's not equal to some claim. So we're going to run those tests a little. Each of these three types of tests, we're going to run a little bit differently. Okay, but getting these hypotheses set up correctly is a really important first step. So let's say we were trying to set up our hypotheses for this example. We've got some cigarettes. Is nicotine content greater than 1 milligram per cigarette? In order to show it's greater than, in my null, I have to assume mu is equal to this claim value. My alternative, Let's look at another example. All right, we want to see, does a new drug, create a change in average systolic blood pressure? Systolic is that top number. All right, so your average person has a systolic blood pressure about 120. Right, so our null is that mu is equal to 120. But what is the alternative here? Right, well here the wording somewhat vague, right? It says create a change in average blood pressure. It doesn't say that this drug is going to lower blood pressure. Hopefully it would, but doesn't say is this drug going to lower or raise. It doesn't have language that pushes us in either direction. Right? It just has general language. Is it going to create a change? So here we may not go for a left-tailed, we may not go for a right-tailed, we might go for a two-tailed test here. Okay, so whenever we just want a general change or a difference, that's where our two-tailed test comes in. Alright, so when we're drawing our conclusion, we draw our conclusion in terms of these hypotheses. Right, remember, we're starting by at the very beginning we say our null is true. Right? But if we evaluate our evidence and we find out that our evidence is strong enough against the null, we'll do what we call rejecting the null hypothesis. Right? But what if we don't find enough evidence? Well, a lot of people would say, okay, well, the opposite of rejecting is accepting. So if I find enough evidence, I reject. If I don't find enough evidence, I accept. Well, no, that's not true. We never accept our null hypothesis. Okay, if I find enough evidence, I may reject the null, but if I don't find enough evidence, we just simply do what's called failing to reject. We're saying, okay, for now I didn't find the evidence against the null, but that doesn't mean that I won't find this evidence in the future. All right, so keep that in mind, rejecting versus failing to reject. Okay, so how do I know? Well, also in the setup of your hypothesis test, you got your hypotheses and you also have your significance level. Okay, our significance level is going to help us determine where to set off that cutoff point for reject versus fail to reject. What makes my evidence significant or not? All right, so your significance level, denoted as alpha, we've seen alpha before. Right? We've seen that in the context of confidence intervals. Alpha was, if I say I had a 95% confidence interval, that meant alpha was 5%. Alpha represented the percent of times that my confidence interval wasn't going to do its job correctly. Right here, alpha will represent percent of time that I'm going to get a hypothesis test wrong in a specific way. So just like with the confidence interval, 95, 90, 99 were common confidence levels. Common values of alpha are 0.1, 0.05, and 0.01. Now 0.05, for whatever reason, is just the generally accepted value of alpha. If we ask, is something good enough or is something significant, statistically significant, usually that 0.05 cutoff is what we go with. Now there's been some kind of debate on that lately, which is kind of interesting, worth looking into, right? But this just kind of arbitrary value of 0.05, right, is usually what we go with. All right, so that covers our first step, getting everything set up. What do my hypotheses look like? What type of hypothesis test am I running here? And what is my significance level? All right, the next step is I'm going to calculate my test statistic. Right, so your test statistic is where we start evaluating our data. Now you may need to collect the data at this point, right, but here's where I start using the data to evaluate my claim. Your test statistic basically tells you how far away is what I observed from what I was expecting in the null. Remember, we're assuming the null is true, so how far away is what I observed, right, from what I was expecting. And we already have a tool for telling us how far away something is, right, when we're dealing with the mean, right, that tool. So in general, we know what a z-score looks like, or the idea of a z-score, and it's very similar to the idea of a test statistic. Right? In general, we take whatever we observe, we subtract the mean, and we scale by the standard deviation or the standard error. Right? Well, here we're going to start by dealing with situations where our central limit theorem holds, we can assume normality, all this stuff, use the z distribution. Okay, well, a z test statistic for the mean would look like this. X bar minus the claimed mean over sigma root n, the standard error there. Alright, so oftentimes this is denoted as z naught. Sometimes I've seen it denoted as zt, or maybe get lazy and just call it z. Alright, so that's the idea of our test statistic. Tell us how far what we observed is from what we are assuming is true. Okay, so what would that mean? For a small value of the test statistic, that means the distance from what I observed to what I'm assuming is true is small. Right? So that's pretty good evidence that the null may be true. But for a larger test statistic, right, that means what I observed is further away from what I'm assuming is true. So a larger test statistic is evidence against the null. Right? Just how much evidence we have is where that cutoff is. Again, that's what alpha helps us set. So we'll see that in the next step. Right? How do we actually make that decision here? Okay. So making this decision, now there's two methods that we can use. There's your p-value method, which we'll talk about next. We're going to first talk about the critical value method, but just a little note on that, the p-value method is preferred typically, but your critical value method is a little more visual, maybe makes a little bit more sense at first glance. Okay, so we start with the critical value method, and then we'll talk about the p-value method. But these are both methods of evaluating your data using my test statistic and figuring out, should I reject or should I fail to reject? Okay, so your critical value method, we need alpha. We find what's called our critical value based on alpha. Now we know what critical values are from confidence intervals, right? So there's kind of some crossover here. That critical value helps us establish our rejection region. Right? That rejection region is also established based on whether it's a left-tailed, right-tailed, or two-tailed test. Then we see, where does my test statistic fall? If my test statistic falls in that rejection region, I reject, right? If it doesn't fall in that rejection region, then we fail to. So how do we find our critical value? Well, it's all based on alpha. Right, so first, we want to find this critical value if it's a z distribution using our table. Okay, so if it's a left-tailed test, we want to find a z value that has the area equal to alpha to the left of it. Right, if it's a right-tailed test, we'll have a positive z value that represents the area to the right of it equal to 1 minus alpha. For a two-tailed test, we'll actually have 2, and we have to divide alpha by 2. Okay, so you'll actually have two critical values. One negative, the one to the left will be negative, but it'll correspond to the area alpha over 2. Your positive critical value will correspond to the area 1 minus alpha over 2. Okay, so once you've established your critical value, then you draw your rejection region. If it's a left-tailed test, your rejection region is the area to the left of your critical value. If it's a right-tailed test, your rejection region is the area to the right of your critical value. If it's a two-tailed test, it's the area outside the negative and positive. Okay, so let's look at an example of how this critical value method works. Well, so let's say we had an example here, a right-tailed test, alpha equal to 0.05. So our critical value for alpha equal to 0.05, we would take this 0.05 to the table. We know our critical value is going to be positive. So the z-score that corresponds to 0.05 to the right of it is 1.645. All right, the area then to the right of that is we define as our rejection region. And this was all because it's a right-tailed test, alpha equal to 0.05. So what if I did the math, I got a test statistic of 3.21. Well, 3.21 would fall over here, so I would reject. Or what if I had a test statistic of 1.24? 1.24 would be in here, so I would fail to reject. Right? So that's how our critical value method lets us make our decisions. Now on the other hand, we've got our p-value method. Okay, the p-value method is a little bit harder to wrap your head around conceptually, but here's an excerpt that I found somewhere that I think does a pretty good job of explaining what the p-value is. Maybe you can take some time to pause the video and read this, but I think it does a pretty good explanation of what the p-value is. Right, so now I'll try my best to explain what a p-value is. Right, so basically your p-value is assuming the null is true. Remember, we have to assume the null is true from the beginning. Right? Your p-value is assuming the null is true, the probability of observing what you did. Right? So if I have a small probability of observing what I did, assuming the null is true, then that's pretty good evidence that null may not be true. Okay, so for smaller p-values, that's evidence against the null. Larger p-values is evidence for the null. We find this p-value from that test statistic. So let's look visually what a p-value looks like. Again, it's based on the type of test we have. If it's a right-tailed test, our p-value is the area to the right of our test statistic. If it's a left-tailed test, our p-value is the area to the left of your test statistic. But of course, two-tailed tests always make things a little bit trickier. Right? If we have a two-tailed test, your p-value is the area to the left of this negative test statistic and the area to the right of this positive test statistic. Now one way of doing it is you could find this area, and you could add them together. Right? But based on the symmetric properties of our normal distribution, we know these two areas should be the same. So the easiest way to do it is just find 1, multiply by 2. So that's where this 2 comes from. So when we have a two-tailed test, we got to remember multiply that p-value by 2. Great. So when we have our p-value, what do we do with it? Well, we compare that p-value then to alpha. If our p-value is less than alpha, we reject. If it's greater than alpha, we fail to reject. Right? So remember what alpha was. Alpha was your significance level. It was the probability of getting your hypothesis test wrong in a certain way. Remember what your p-value is. Your p-value is the probability of observing what you did, assuming the null is true. Okay, so basically what we're saying here is if the probability of observing what you did, assuming the null is true, is less than the probability that you were going to get it wrong in the first place, right, well, that's pretty good evidence against the null. All right, so that's where we come up with this criteria. So again, our steps are, we state our hypotheses, just summing all this up as our null and all alternative. We get everything set up, including our significance level. Right, then we calculate our test statistic. We make our decision with either method, and then we'll draw conclusions. And if you watch our next video, we'll do all this, put all this together in the context of an example. All right, so thanks for joining, and we'll see you next time.